All right, let's get into it. Today, you're not just a student, you're a chemical detective. We're going to grab our lab coats and solve a mystery, unmasking the secret identities of ions that are hiding in plain sight. Ready? Let's dive in.
So, picture this. Someone hands you a test tube. Inside, there's this liquid. Could be clear, could be colored. You know there's a metal ion, a cation, hiding in there. It's the culprit. So how do you figure out what it is? Where do you even begin? Well, that's the exact case we're cracking today. Okay, here's our game plan. First, we'll cover the basics, Chemical Detective 101. Then we'll check out our detective kit, the alkalis. After that, we dive into the case files, starting with sodium hydroxide, then ammonium hydroxide. We'll even look at a cool plot twist, the amphoteric twist. And to finish it all off, you get to solve the final case. Let's go. All right, Section 1. Every great detective knows the first rule. Observation is key. So before we start mixing anything, the very first thing we do is just look. You'd be surprised. Sometimes the suspect basically just gives itself away with its color. So yeah, a lot of these salts are colorless, totally boring. But these guys, the transition metals, they're the flashy ones. They practically announce themselves. See a blue solution? Your brain should immediately scream copper. A light green one? That's almost certainly the ferrous ion. Just by looking, we've already got a massive head start in our investigation. Okay, so visual clues are great, but to really crack this case, we need to apply some pressure. Get a confession. In chemistry, our pressure comes from reagents. And in our detective kit, we've got two essential tools for the job, a couple of alkalis that are going to make these ions spill their secrets. All right, let's meet the interrogation team. On one side, we've got sodium hydroxide, NaOH. This is your tough interrogator, the bad cop. It's a strong alkali, and it gets a reaction from pretty much everyone. Then you've got ammonium hydroxide, NH4OH. This one's the specialist, the good cop. It's a weak alkali, so it's a bit more subtle. It can pull out these really specific, unique clues that the tough guy might just bulldoze past. Using both of them together, that's how we solve this thing. Okay, time to open the first case file. We're bringing in the tough interrogator, sodium hydroxide. Here's the plan. We take our mystery solution and we add the NaOH, just drop by drop. What we're looking for is a precipitate. That's just a fancy word for an insoluble solid that forms. The color of that solid, well, that's our next huge clue. And boom, check out these results. Each suspect reacts by forming a solid, a metallic hydroxide with a super distinctive color. See a dirty green precipitate? That's basically the ferrous ion screaming its name. That reddish-brown one? Oh yeah, that's ferric. Pale blue? Has to be copper. Just like that, our list of suspects just got a whole lot shorter. But wait a second. We've hit a snag. Look here. Calcium, zinc, and lead. They all give us a white precipitate. So now what? Are we stuck? How in the world are we supposed to tell these three apart if they're all giving us the same exact clue? This is where it gets interesting. This is what separates the rookies from the pros. A good detective always asks a follow-up question. The real secret isn't just seeing the precipitate form. It's what happens next. We're going to keep adding our sodium hydroxide. We're going to add it in excess. Let's see if that white solid is stubborn and stays put, or if it dissolves. And here's the payoff. This one simple trick cracks the case wide open. The calcium precipitate, it's tough. It barely dissolves. But look at this. The zinc and lead precipitates, they totally disappear. They dissolve in that excess alkali. That is a huge difference. We've just positively identified calcium and narrowed it down to our final two suspects, zinc and lead. All right, time to call in the specialist. We're opening the case file for ammonium hydroxide. Remember, this is our weak alkali, so it's going to give us different, maybe even better clues. This is how we're going to finally nail down those last tricky suspects.
Okay, now you've got to pay close attention here because these results are different from what we saw with NaOH. See lead? Remember how it dissolved in the strong alkali? Well, with this weak one, it stays as a solid. It's insoluble. And that is how we finally tell lead and zinc apart. Because the zinc precipitate, it does dissolve. And then there's copper, which does something amazing.
I'm not kidding, the test for copper is one of my favorites. It's one of the most classic, most satisfying moments in all of basic chemistry. When we add excess ammonium hydroxide to that pale blue solid, just wait, something absolutely incredible happens. This is the smoking gun.
The solid just vanishes, and the whole solution turns this incredible, deep, inky blue color. It's gorgeous. What you're seeing is the formation of a special complex ion called tetraamine copper 2. If you see that color, that's it. Game over, case closed. Your suspect, 100%, is the copper ion. There is no other explanation. It's a signature move.
Okay, so we know what happens, we've seen the evidence, but a truly great detective needs to understand the why, the motive. So, why did zinc and lead dissolve in that excess strong alkali when the others didn't? The answer is this really cool chemical property. A little twist in the story.
It's a concept called amphotericism. Think of it like this. Most of these hydroxides have a one-track mind. They're basic, which means they react with acids. Simple. But an amphoteric hydroxide, it's got a dual personality. It's like a chemical double agent. It can act like a base and react with an acid, or it can flip the script, act like an acid, and react with a strong base.
And this is what brings it all together. Zinc, lead, and also aluminium hydroxides are our main amphoteric suspects. So when we first add just a little bit of strong alkali, they play their base role and form that solid precipitate. But when we overwhelm them with excess alkali, they switch sides. They play the acid role and react with the base, and poof, they dissolve. That's the secret behind our excess test. Pretty clever, right?
Okay. You've seen the techniques. You've examined the evidence. Now it's your turn. You are the lead detective. I'm going to lay out the clues for 3 final cases, and it's up to you to name the suspect. You ready for this? Let's do it.
Here we go. Case number 1. Your starting solution is a pale green color. You add your tough interrogator NaOH, and you get a dirty green solid. And it's stubborn. It doesn't dissolve in excess. So, who's the culprit? Got it? If you said the ferrous ion, Fe2+, you are spot on.
All right, case number 2. This time, you've got a colorless solution. You bring in your specialist ammonium hydroxide. You get a gelatinous, kind of jelly-like white precipitate, but when you add more, it completely dissolves. Who is it? Think about it. That's right, that's the classic test for the zinc ion, Zn2+. Awesome job. And now for the grand finale. Case number 3. You start with a blue solution. You add your ammonium hydroxide. You get a pale blue solid. And then you add a little more, and the entire thing transforms into that incredible, deep ink blue solution. Come on, you know this one. Who is it? It's gotta be the one and only copper ion, Cu2+. You nailed it. And just like that, case closed. You actually did it. You used your powers of observation. You understood how to use both strong and weak alkalis, and you unmasked every single suspect. You've officially mastered the art of being a chemical detective. So, there you have it. It turns out that with just a couple of simple chemicals and a sharp eye, you can solve some pretty cool mysteries. You now have the skills. You're a chemical detective. So the only real question is, what mystery are you going to solve next?